Okay, great. I want to share my screen. And can y'all see this image, this applet here in the middle? Let me know in the chat or some kind of way whether or not you can see this image. If somebody could let me know whether or not you can hear me, I sure would appreciate it. Oh, thanks, Edgar. So Edgar, can you see this applet on the screen? Yay. We talked on Wednesday about the dot product between two vectors. And we said that A dot B was the magnitude of A times the magnitude of B times the cosine of the angle between them. And what we're going to see is that the cross product is a vector. The dot product is not a vector, the cross product is. And it is the magnitude of A times the magnitude of B times the sine of the angle between them, and then in the direction of the normal or the perpendicular to both A and B. And we'll talk about how to figure that out in a sec. There's another, I think this is not it. Oh, here. Oh, this is the same one. Well, I had another one that was kind of cool. Let's see if it was this one. Not sure why, but my computer is very slow this morning. No, this is, I'll find it later. But I just wanted you to see that the cross product is an entirely different kind of thing to the dot product. So let's just remember, if we have vector A and vector B, and here's an angle theta between them. Then A dot B is the magnitude of A, the length of A, I didn't mean to put a dot there, times the magnitude of B times the cosine of the angle between. And magnitude is just length. So if A is, let's write it this way, XA, YA, and B is XB, YB. So just the standard notation for A, where this means that we're starting with the tails, both tails at the origin. Then the magnitude of A is the square root of the x coordinate squared plus the y coordinate squared, and the square root of that whole thing. Similarly for B, and then the cosine of the angle between them is just this angle. And you can see that magnitude or length is a scalar. We no longer have any direction involved here. What's interesting about the cross product, and I want you to think of this in general before we look at the nitpicky parts of it, is that if you have, let's see, right here, if you have vector A going in this direction, so let me see, I'm going to orient so that I'm looking at this, and I have to redraw it because I can't go backward. If we have vector A and vector B, then we can visualize the cross product as if we take our right hand and put the fingers along A, then curl in the direction of B, your thumb is going to be the direction of the cross product. So if you have A cross B, then in this example, where we've got A cross, so we start with A, that's how we get the direction for the fingers. Then we've got B, that tells us which direction to curl our fingers. And we've got our thumb that shows us the direction of the cross product. And so you can see that even though A and B can live on the plane, they can be two-dimensional, the cross product is not going to be, it will not stay in the plane ever. And a thing that's really pretty to do, so remember that we had a unit vector I, which was 1 unit in the x direction, and a vector J. Unit vectors always have these little hats. J is 1 unit in the y direction. you can see that I and j are vectors. And let's see what I cross j looks like. So let's see, start with our fingers along the first one. So we started with I, fingers along I. We wrap towards, fingers curled toward J. The answer is up. And you can, maybe you can see that we are indeed describing the K vector, which is one unit along the z-axis. The way that we find cross product, there are a couple of ways, but the standard way that we start with is we've got, let's see, let's write A. Remember that we had x sub A, x sub Y for A, and x sub B, y sub B for vector B. I could write, I could use the unit vectors and these coordinates to write A as x sub A in the I direction plus y sub A in the j direction. And similarly with B, I can write B as x sub B I plus y sub B j. So here A is in 2 dimensions, just I and j. B is in 2 dimensions, just I and j. They both, because they both only have I and j, we know they both live on the plane. So let's see, let's copy that here. X sub B I plus y sub B j. X sub A I plus y sub A j. So then the cross product is equal to the determinant of, well, first we write down the directions. So the top row is going to be I, j. The second row is going to be and I think I'm being an idiot. Just one sec. Oh, no, this is right. Okay. So we've got I, j in the first row. We've got x sub A, y sub A in the second row. And we've got x sub B, y sub B in the third row. And the easiest way to figure out, let's not do it the easy way first. Let's just look at how you find the determinant. So there's one basic thing to remember. If we have A, B, C, D, where we're thinking of A, B, C, D as a matrix. The determinant is like not the absolute value, but a quantity that we can assign to a matrix. And we find, if we have 2 rows and 2 columns, we find the determinant as A times D minus C times B. So it's the diagonal, the major diagonal minus the minor diagonal. But we have kind of a weird setup. That's okay, because what we're going to do oh, yeah, duh. So for us, doesn't matter which one of these we choose, we're still just going to find x sub A, y sub B, minus x sub B, oh, this should be a y sub B, and this is an x. Good grief, I don't, oh, no. Oh, you guys, I'm just, okay, I'm gonna rewrite it. I apologize for that. So here we go. If we have x sub A, y sub A, the 2 coordinates of A, and x sub B, y sub B, the 2 coordinates of B, then the determinant of this matrix is x sub A times y sub B minus x sub B, y sub A. And you notice we lost our directions, but because we are in 2 dimensions, there's no option for the direction of our answer. This amount here will be in the direction of K. So if A and B are in the plane, so 2-dimensional, then the cross product, and cross products are vectors, the cross product is, you put the coordinates of A, you put the coordinates of B, you find the determinant of that matrix, so primary diagonal minus the minor diagonal, and the direction is going to be in the K direction. What if in the same drawing, what if we were trying to find B cross A? then we always you use your right hand. Start with B. Oh wait, I can't curl in the direction of A. Oh, I see. So in order to curl in the direction of A, I put my fingers out along B, curl in the direction of A, and the resulting vector goes into the plane. So we would say that this has direction negative K. So if in moving from B to A, if in moving from the first vector to the second, you're going clockwise, then it's you always have to use your right hand. Then the direction will be into the plane. If you're going counterclockwise, A cross B, the direction will be out of the plane, so positive. So that's illustrated here. And magnitude, the magnitude of the cross product is almost the same as the magnitude of the dot product. We're going to take the magnitude of B multiplied by the projection of A perpendicular to B. Oh, wait a second. We didn't talk about projections. Well, let's see. So if I've got a vector A and a vector B, and I want to find the projection of A onto B, that just means I want to find like the shadow. Of A onto B. So if the sun is above B, going down, then it is exactly the case that the projection of A onto B will be this shadow created. And let's see, we've got a triangle. Angle theta. I know that since this is vector A, I know that the length of this vector is the magnitude of A. And that means I know how to write these other two sides. So it's little a and little b. I know that the cosine of theta is little a over the magnitude of A. So I can find little a by multiplying both sides by the magnitude of A. So the projection here will be the magnitude of A times the cosine of the angle between vector A and this vector B. It's the amount of A going in the direction of B. And let's just play with this formula for a sec. Do y'all remember last time we said that if we have two vectors A and B, we can find the angle between them as the cosine of theta is A dot B divided by the magnitude of A times the magnitude of B. And that is not supposed to be there, sorry. So let's replace cosine theta with this mess. Okay, so we've got, this is all little a. Little a is equal to, we're going to leave the magnitude of a, but we're going to write the cosine of theta like this. So the dot product of A and B divided by the magnitudes of A and B. And hey, cool, we can divide out the magnitude of A. And so this is a formula that you will often see. And let's write it in the way that you'll see it. You'll have, the notation is the projection of A onto B. So this is of A onto B. So I would say little a is equal to projection of A onto B. And we're going to write it this way. We've got vector B over its magnitude. And we're going to dot that with A, because dot product is commutative. There's no direction in dot product. We just have scalar numbers. So this is a formula that you'll see a lot. It's not anything you need to memorize. But projections, one of the uses of projections is like if you're out doing good deeds and an elderly woman is hauling a wagon up a 20-degree incline. And say she's got rocks in there. And the whole wagon is, I don't know, 40 pounds. The amount of gravity pulling on that is not really in the backward direction. Gravity is down. So to figure out how much gravity is acting on our little situation, we need to find we're going to think of 40 pounds as a weight. So let's do this in metric so that's easier. So let's say that we have 40 newtons. You always capitalize newtons. So we've got 40 newtons. That means we've got a force going uphill, but how much are we having to fight gravity? Well, gravity is going to be, see if we think of this as a vector. Then we've got the projection of 40 newtons with the ground. So let's say that the ground is 0. We don't need anything for that. In fact, let's use this formula. This formula. The one with, here it is, with cosine. So we've got the magnitude of 40 newtons times the cosine of 20 degrees. And that'll tell us how much of this mass going uphill we're actually having to pull to fight gravity. I'd like to revisit a little bit more of cross products and applications of dot products and cross products on Wednesday. I'd like to have a short class on Wednesday and just look at some applications, and I will answer any questions that you have over the practice final. So let's take a 5-minute break.